Okay, welcome guys. So this video, let's just deviate a little bit, talking about a counting principle or counting formula. Okay, so what I want to prove is that if H and K are both a subgroup of G, and one can define a thing called HK, right? So basically it's HK, H belongs to H, K belongs to K. Okay, so I want to investigate in what sense, in what case, HK is a subgroup. Okay, so this is the interesting points. If you guys can try, you can try some examples that just to show that HK and to show that HK may not be a subgroup. Okay, so let's talk about theorem. So theorem says that HK, if let's say if HK equals to KH, if and only if HK is a subgroup. Okay, so this is what I originally want to prove. Okay, so let's see the proof. So proof should be, let's say we prove these directions. Suppose HK equals to KH. That means that means what? That means HK will equals to K1 and H1 and H and H1 in H, K and K1 in K. Okay, so we need to prove that HK is a subgroup, right? So by the previous lemma, we need to show the closure. Okay, so the closure, let's say suppose X equals to HK in HK, and Y is another one, right? So we need to show that their product, right? So their product XY it will be HK, H prime, K prime. We need to show this is in HK, right? But you see this KH prime, right? So KH prime is in KH, right? But HK is in KH, right? So this tells you that this guy is in HK, right? But this guy is in H, right? So this guy will be in HK because this guy in H, this guy in K. Okay, so done, right? And also let's call it about inverse. So inverse is also easy. So let's say X inverse, right, will be HK inverse, right? So will be K inverse H inverse, so will be KH, right? But KH is the same as HK, so so X inverse in HK, right? So now we prove the closure and the inverse, right? Which tell you that HK is a subgroup. Okay, so let's see the next directions. So next directions tell you that we need to show that we need to show what if HK is a subgroup. Is a subgroup of G, then HK will equals to KH. And this is what we want to prove. Okay, on the other, so this is let's say that let's say HK, right? It's the elements and its inverse. Basically, it's just K inverse H inverse. Okay, so notice that the KH inverse is basically H inverse K inverse inverse. Okay, by the way, and this belongs to HK, right? So this belongs to HK. So here tell you that what? Tell you that each, so you see each KH inverse will be in HK. Okay, each KH inverse will be in HK. Sorry, that KH is KH, right? KH. So each KH will be in HK. So which tell you that KH is a subgroup of HK. Right, because KH is H inverse, K inverse, inverse, and HK is a subgroup, right? So KH will be sit in HK. Okay, so if you have element in HK, your X inverse, so X is HK, right? And then your F inverse will be K inverse H inverse. So this will be in KH. This is in KH, right? So this tell you that the HK will sit in KH. Right, so from these two, you know that HK must equals to KH. Okay, so this is just a proof. Should be the, I think should be easy, right? Because just write down a definition. Let me just clean the note to make everything clear. Okay, so maybe I change your color for fun. Yeah, so this KH is H K. Yeah, So yeah, this is right. Yeah, so the proof is done. Okay, so now the corollary, so simple corollary, if HK are abelian subgroup, of G, then HK is a subgroup. Subgroup. Okay, and the reason is trivial, right? Because in this case, HK will be KH. Okay, and that's just talking about finite final results. That's called counting formula. Okay, so if let's say G is finite, okay, so G okay, so G may not be finite, but the H and K are finite. So you take any two subgroup of G, which both are finite. Then what is the order of this HK? Right. So the fact is that the order of HK will be order of H times order of K divided by order of H intersection K. So notice in this case that HK may not be a subgroup, right? Because I'm not saying that KH the same as HK. I only say that HK is a set, so may not be a subgroup. Okay, so this is the what I intended to prove. Okay, it's the final part in this video. Okay, so the proof that's talking about special case. So the special case will give you an idea that why this is true. So suppose that H intersection K is only identity. So I want to show that HK equals to the order of HK will equals order H times order of K. Okay, so the proof should be, let's say, so what is the case that this will not happen? This will not happen means that there exists H and K and the H1 and K1 such that H may not be the same as H1 or K not as the K1, but you have HK equals to H1 K1, right? So that means there's a collision. Okay, but from here you know that H inverse equals to, sorry, so you have a H inverse H equals to K1 K inverse, right? But this belongs to H, this belongs to K, right? And but their intersection is only identity, so which tell you that H inverse H must be K inverse must be equal to identity, which tell you that H1 must be equal to H and K1 must equal to K. So which just indicates our results, right? Because there's no collision. Okay. So let's talk about general case. Okay. So general case tell you that general case what it means. Okay, so that means how we need to ask how often HK happens in HK. So that means if you write down the products of HK, write down a list, write down a table, how many times that the HK will be the same as previous one, right? So the claim is that the HK always happen at H intersection K times. So this is what we want to prove. Okay, so the remark, just see the remark. Let's say if you have H1 is H intersection K, then your HK will be H1 H1 inverse K, right? So right, but this is H1, this is H, right? And this is H, and this is, so H1 is indeed, right? So this is H, and this is K, right? So HK, so from here that you see that HK will duplicate H intersection K times, right? By definition, because you can take any H1 and times H, and then you can take any H1 inverse times K, okay? Okay, so that means okay, so this is the one direction. The other direction is that suppose you get HK equals H prime K prime, then you always have H inverse H prime equals to K inverse prime, K prime inverse, right? Just write down. So from here that you call U, right? So you know that now U is intersection in H intersection K because this is in H, this is in K. Okay, so that means if you have any collision, then you already counting in this way. Okay, so that means that means you always count H, at least count, at most count H intersection K times. So finally, you just need to show that they're distinct, right? But this is trivial. Okay, because H inverse is distinct, right? If you use different H1. Okay, so let's talk about the corollary. Okay, so corollary is that if H and K are both finite group, also are both finite subgroup of G, and the H larger than square root of G, and the K larger than square root of G, and their intersection cannot be identity, or cannot be one. Okay, the proof. Okay, so since that we know that G is greater than HK, right? Because G is HK are both subgroup of G, it's basically H and K and H intersection K, right? But by definition, this is greater than G, H intersection K, which tell you that H intersection K must larger than 1 if you clean G here, right? So let me just write down, write careful. So this is okay. So you know that H intersection K must greater than 1. Okay. Yeah. So very simple corollary. Okay. Yeah, so this corollary can give a very special results. So the application. So this application we will use in the by CO theory in the future. But actually, you can do this. Suppose G is finite order of P and Q, which P, Q are prime. P is greater than Q. Then I claim G has at most one subgroup of order P. So G has at most one subgroup of order P. Okay, and the reason is simple, right? Because if H and G, if H and K are both or subgroup of G with order P, then you will get what? You will get the H intersection K cannot be identity, right? But the problem is that, well, since if HK are both subgroup of G with order P, then they are set. Then this just translated into H greater than square root of PQ, K greater than square root of PQ, right? But then H intersection K cannot be identity, right? But H is a prime power, K is a prime power, right? If their intersection cannot be identity, that means H must be equal to K by Lagrange theorem, right? Because their intersection must be a subgroup, right? But by Lagrange theorem, that subgroup order must divide H and K, but H and K are both prime number, right? So H must be same as K. Okay, so that's it. In the next video, we talk about the normal subgroup.